Muhammad. Today I'm going to speak further about the 4x4 magic square. I uploaded a video recently that introduced the magic square of order 4, but there are a lot more points which have to be explained about it. So today in this video we will be looking at the so-called magic square of order 4, or the 4x4 magic square, and taking a closer look at it. So you might recall that when we studied the 3x3, there were 4 different kinds or 4 different sequences of filling the 3x3 square, and each of those corresponded to one of the 4 elements of ancient science, namely fire, air, water, and earth. Now, we're going to do the same today with the 4x4. And just as with the 3x3, we looked at what you do when you end up with a remainder, when you want to encode some number in that square. If you end up with a remainder, how do you deal with that remainder so that you still sum up to the so-called magic constant? The 4x4, the 4x4 wifq, or the 4x4 magic square, is extremely important in Islamic Quranic theurgic practices because it has this four-sided relationship, so to speak. It's a ternary, and therefore it goes very well with the concept of the 4 elements. Many divine names also have 4 letters in them, and so that's also important in some kinds of magic squares. Now, if we look over here at this diagram which I have made, if we have any kind of a 4x4 square, this is how the elements are distributed in the different cells of the square. So we have here, beginning with F standing for the fire element, then air, then water, then earth. And then this top row is then changed in the second row so that you are basically reading it, you're reversing the direction. You see, you have fire goes over here, then you air, then water, then earth. Then down here we flip these two, fa, F-A, fa, W-E, we, if you want to say, or at fire and air, and then water and earth. And again, then you take this and then you flip this and bring this here, and you flip this and bring this here. So this shows you how the elements are distributed in the 4x4 square. And the basic or default 4x4 square corresponds to the fire element, and I have indicated it here. So if we look at it, we have 1, the number 1, and it starts here at the fire square, so to speak, the fire cell. And then you do a knight's move and you come down and you put in a 2, which goes in water. Then you come down here and you do a 3, which also ends up in water. But after that, it doesn't matter. It's where you begin. So then you come over here, 4, then you put 5, knights move up 6, 7, knights move up 8, knights move come all the way down 9, knights move down 10, knights move up 11, knights move over here to 12, then you have to put the 13 over here, 13 is followed by 14 in this square, 15 goes all the way in the bottom, and then you're left with 16, your knights move up there, and this is the basic default number. Now, I think I explained before that the so-called magic constant for this square is 34. Let's just check. So if we start here and go down, 1 plus 12 is 13. 13 plus 6 is 19. 19 plus 15 is indeed 34. And you can verify that this square actually, I will leave this as an exercise for you to work out, that it actually does sum to 34 every way. In other words, every horizontal row, every vertical column, and both diagonals sums to 34. Perhaps we should look at the diagonals. Remember, there's an issue with diagonals sometimes. Let's make sure that nothing's going wrong here. So we have 8 and 2 is 10. 10 plus 9 is 19, and then 19 plus 15 is again 34. If we go with the other diagonal, 1 plus 7 is 8. 8 plus 16 is 24, and 24 and 10 is going to be 34. So you see that everything is working out very nicely here. Now then, given this arrangement of fire, air, water, and earth across the top row, we can theoretically then prepare a magic square based on air if we place the 1 here. And that would simply involve just rearranging the columns. So if we call our columns, if we call this column lowercase a, and this one b, and this one c, and this one d, all we're doing is we're taking what would here be the column, the A column, and we're putting it here for air. We're moving it into the B column. And then we're flipping C and D with each other. And then, of course, the A column would then take what was here the B column. But I think you understand what I'm doing. So we're taking this vertical column here and we're putting it in this place. And then we're taking the column that starts with 14 at the top and putting it in this place. And we're taking the column which begins with 8 here and we're putting it where the 11 is. And then we're putting the 11 column over here. And so by similar manipulations, you could then have your water square arranged this way with the 1 in the water position. And again, you're doing some manipulations. So what's actually been done here is this whole half portion has been taken over here, and then this whole half portion has been picked up and put over here. Maybe I can make that clearer. In other words, if you see, where'd we go? Ah, yes. So you take this whole portion, for example, and it's moved over here. And then the remaining part is just moved over there. Then to get the earth square, you see you have the 1 in the earth position. You've done similar manipulations. You take the 1 here, the column that is headed by 1, and then you switch it with the 14 over here. And then again, you switch the 8 and 11. So you've swiped these two, and you swipe these two. Maybe I think I meant to say swapped, but I think you know what I mean. So let's put this pen away. So this is one way of doing it, but in particular, there are differences among people on how they do this. Typically, most people do not go according to this method. And the method they do go according to is illustrated here below. So the fire, as it's given here, is exactly the same. It remains the same. But with air, we put the 1 down here. And if you look in our original chart up here, air is in this position. And then for water, the 1 position is moved here, so it goes down there. And earth moves all the way down to the bottom, so that's also earth. So if we look at this square, we've already looked at the fire arrangement. If we look at the air arrangement, we have our 1 here, then 2 will go down using a knight's move, then 3, then 4, 5, 6, 7, 8, 9, and all the way over here up to 10, then all the way down here 11, 12, 13, up, knight's move 14, 15, and then all the way down here 16. So similarly, by similar movements, we start with the 1 here in the water square. We go over and have a knight's move, and that gives us our 2. We go all the way up and we have 3. Knight's move, we have 4. Then we put the 5 next to it. Go up with a knight's move 6. Knight's move all the way down 7. Knight's move up here 8. Knight's move 9. Knight's move 10. Then 11. Knight's move 12. 13 has to go here. Knight's move up to 14. Then 15 has to go here, and knight's move gives us our final position of 16. So with the earth, we start on the bottom again. This corresponds to earth. Then we have 1, knight's move 2. Then up here 3, knight's move up 4, 5. Knight's move down to 6, 7. Knight's move down to 8. All the way up 9, knight's move 10. All the way down here 11, knight's move 12. 13, knight's move down 14. Up here 15, and knight's move 16. So these are all the different arrangements, if you want to say the so-called standard arrangements. This is how one of the most famous Quranic theurgists of the Indo-Pakistan subcontinent, this is the system he followed. His name is Qash al-Barni. He wrote a very famous book called Amil-i Kamil, but it's in Urdu. So if you read Urdu, this is a good book to refer to. it's not very well organized. I think that's on purpose. But there is a lot of useful information arranged throughout the book. So this is our basic 4x4 square. Once again, the default is this fire. And in both systems, the fire arrangement is the same. But here lower on these larger squares is the so-called, what I'm calling the standard system. We have the arrangements then of fire, air, water, and earth. Now, I would like to deal with a question which someone posted on the channel. And even though these markers can sort of leak through, we can still use this paper. This has a bit less leak through on this side, so let's do this. Now, the person asked me that, well, all right, when you talked about the 3x3, remember, in the case of the 3x3, we take whatever number we want to use to encode in the square, and we reduce it by 12. So, for example, we did the divine name Allah, and Allah has the value 66, and it had to be reduced by 12. And once it's reduced by 12, you get 54, and then the resulting number, 54, it has to be divided by 3. And when you divide it by 3, you get 18. And the resulting number is the number that you began with. And so if we had our 3x3 like this, for example, we would start, if we start on the bottom, for example, we put the 1 here. 1 would have been here. Let me just show you the pattern. It would be 1, 2, 3, 4, 5, 6. And then you would have 7, 8, 9. And everything adds to 15. So if we followed this pattern, and we did this before, but I'm just making a point. We've done this in earlier videos, so you understand. So this would be 18. 18 would be the 1 position. You go up to the 2 and you increase by 1. 19, 20, 21, 22, 23, 24, 25, and 26. Now the question which this person asked was, okay, in the 3x3 you subtracted 12. In the case of the 4x4, you don't do that. In the case of the 4x4, you have the number, let's do it again, let's just say that the divine name Allah, let's say we have 66. Well, 66 here has to be reduced by a different number, and it has to be reduced by the number 30. And if we do that, then we get 36 as the answer. Then 36, this number has to be divided by 4. And if you divide by 4, you get 9. So the question that the person asked was, how come with the 4x4 you subtract by 30, and with the 3x3 you subtract by 12? And they said, what is the logic involved here? Well, you have to remember the general formula. There is a rationale. So we have every magic square. It doesn't matter what size it is. We can say that if for any n by n magic square, the magic sum S is given by this formula. So here, the magic sum, we wanted to get 66 in either of these. And so that is the number S. That number S will be equal to the initial value times the dimension of the square, which is the n by n, plus the skip constant. Here we're skipping by 1. You see, we're counting by 1s. 1, 2, 3. We could count by 2s. So that's the number given by beta. Then you have n here again. Beta times n over 2 times the quantity n squared minus 1. And obviously, you can't have a 1 by 1 magic square. You can't have a 2 by 2 magic square. I mean, you can make a grid like this, but there's no such thing. So it has to be 3. So n is greater than or equal to 3. The smallest magic square is 3. So now, if you put in some value here, let's say if we want to look at the 3x3, what happens? Well, then that means that that n, we're going to put in 3 for n, okay? And we're counting by 1, so we're going to put in a 1 for the beta. And A, this is the minimum value where we want to start. It's the minimum value. Now, in the default squares, you always start at 1, but you know, if you have 66 or 72 or whatever number you want to encode, you can't start at 1. So let's see what happens to the formula. So for the 3 by 3, you will have S. This is for n equals 3. That means the 3 by 3. For the 3 by 3, you will have that S is equal to A times 3. So it'll be equal to 3, because n is 3, 3A, plus, this is 1, so it doesn't mean anything, and n is 3 over here. So it's 3 over 2 times 3 squared minus 1. So what happens there? Well, what's 3 squared minus 1? Let's just work out this little bit here. It's 9 minus 1. And what's 9 minus 1? It's 8. So this whole value here is going to be 8. And then you're going to have 8 divided by 2, which is 4. Then when you're left with 4, it's going to be 4 times 3, which is 12. So the S, this will end up equaling 3A plus 12, right? Because we had 8. 8 divided by 2 is 4. 4 times 3 is 12. This is the value for the S. We had an S over here. Let's write it like this. So it means that whatever number you want to end up with, you have to take that number and subtract by 12 and then divide by 3. That means you're solving for A. So here we wanted to get the minimum value. If we had 66, we want to know what number do we start at? We know we start at 18. And that's the number A here. So if we solve this equation for A, that means 3A plus 12 equals S. Subtract 12 from both sides. So you have S minus 12 is equal to 3A, or A equals S minus 12. You know, the number you want to encode divided by 3. And that's why you subtract by 12. So whatever number you want. Let's say if you had 72, then you would take 72 minus 12. 72 minus 12 is 60. 60 divided by 3 is 20. And so you would have to start for the 3 by 3 with a minimum value of what? What did I say it was? 72 minus 12, 60, 20. You would have to start with 20. Let's flip this over. What if we have n equal to 4? Well, that's the 4 by 4, right? If you have a 4 by 4 magic square, this means that n equals 4. And so we come back to the formula. S is equal to, now it's upside down, but it would be 4 times A plus, again, 4 over 2 times 4 squared minus 1. And you get S is equal to 4A plus, what's 4 divided by 2? Well, it's 2. 4 squared is 5 minus 1 is 4 times, 4 divided by 2 is 2. 4 squared is 16. 16 minus 1 is 15. So this becomes 4A plus 2 times 15 is 30. Aha! And that's why you subtract by 30, because again, remember if we had 66, then we took 66, we reduced it by 30, we got 36, and we divided by 4. So here, if you want to solve this for S, you subtract 30 from both sides, so you have 70 minus 30 equals 4A. Then solving for A and flipping around the equation, you have S minus 30 divided by 4, meaning whatever number you want to end up with, you must reduce it by 30 and then divide by 4. This is not fortuitous, it is not random, it is mathematics. So the subtraction factor here is 30 for the 4 by 4. So this is all based on very precise mathematical principles. We will be doing another video at soon, inshallah, on the 5 by 5. But let's just see what happens. If you have 5 by 5, what would be the subtraction factor? So a 5 by 5 means n equals 5. We come back to our same equation. So S is equal to 5a this time, the minimum value, 5a, plus, what's it going to be? Again, we're counting by 1, so it will be 5 divided by 2. And then we have to take our n, which is 5, and we have to square it, then we have to reduce by 1. Yeah, because it's an plus beta times n over 2 times the quantity n squared minus 1. So let's see if we done. Is that right? Yes, n is 5, so that's a 5 over 2. Correct. So now let's simplify what's in here. This is going to be 25 minus 1, which is what? It's 24. So let's write that in. So we have 5a plus 5 over 2. Let's leave everything this way. 5 squared is 25 minus 1 is 24. Okay. So now let's divide 24 by 2. What do you get? You get 12. So you get 5a plus 5 times 24 divided by 2 is 12. And so it's 60. 5a plus 60. So the subtraction factor there is going to be 60. So this is what is involved in the mathematics of magic squares. Now, what I would like to do for you is we will look at some examples of how to encode certain numbers into the 4x4 square. Now I'm going to show you how to deal with remainders with the 4x4. We already did in the previous video when we first introduced the 4x4 an example where we didn't have a remainder. So now I'm going to show you some examples in which you will get a remainder. So first of all, what are the rules for the remainder? If in dividing by 4, you're either going to have a remainder of 1. If you have a remainder of 1, then you will increase by 1 the value in the 13th cell. So you would go here, for example, I have an empty 4x4. Whatever the value is, you would go, here's the first, second, third, and then when you get to the 13th cell, you would increase the value by 1. And then you would keep counting by 1s from that value. So then you'd go to the 14th, the 15th, and the 16th. All right? So if you have a remainder of 2, this means that you would increase by 1 in the 9th cell. And then if you have a remainder of 3, then you will increase by 1 in, ran out of space there, in the 5th cell. That's a 5. In the 5th cell, okay? So that's the procedure you have to follow. So I'm going to do 3 examples, all right, where we'll have each of these kind of remainders to show you what is happening. Mm-hmm.
Let's move this closer. Is that fine?
So let us then begin with an example where you have a remainder 1. Now, I strongly urge that you stick to one of these patterns when you're learning. So this is the pattern according to the fire arrangement. And I strongly suggest that you get some graph paper. I don't have graph paper this large, so I had to draw my grids. And that's why they're a little bit, they're not too straight, but it's enough to explain the concept. But you should try and work with some graph paper. Because the larger you go, the bigger and bigger the squares, it's very easy to lose your place and find out, and keep track of which row or column you're in. It's easy to go over 1 or 2, and it makes a huge mess. So then you should put out the pattern that you're going to follow. So I've put 1, 2, 3, 4 according to the fire pattern so that I don't get lost. So let's say we wanted to do something like the divine name Salam. So that has 1, 2, 3, 4 letters, and they are Sin, they are Lam, they are Alif, and they are Mim. So here we've more or less written it in some sort of pseudo thuluth-based some sort of thuluth-based handwriting. This is roqa-based handwriting. So sin is 60, 31, and 40. In other words, if we write it in English, it's 60. Sin is 60. Lam is 30. Alif is 1. And mim is 40. Now, if you add all of that up, what do you get? You get a 1 in the ones column. 6 plus 3 is 9, plus 4 is 13. So you get the value of 131. Remember what the subtraction factor is for the 4x4? It is 30. That's easy enough to do. What do you end up with? You end up with 101. Now, if you want to divide 101 by 4, it doesn't divide evenly. So we know that 4 25s would be 100. And that will leave 1. So we have a remainder denoted by R of 1. So what does that mean? Well, that simply means that our minimum value, our start value, is 25. And since we have remainder 1, when we get to the 13th square, which will be here, I'm going to put a big circle in here to remind me so I don't forget. And I'm just going to start counting from 25 in the 1 position. So we put our 25 here. Knights move over here. 26, 27. We're counting by 1. 28, 29, 30. So far, so good. 30. 31, 32, and 33, 34, 35 in the 11th position, and 36. Now we're in position 12, and we're moving to position 13. So what do you put here? You don't put a 37. It's 36 here, so it would be 37. It would be 37, but we're not going to write in a 37. We are going to write in a 38. So we have 38 here. Then we go to the 14. 13 is here. Then we go to 14 position, which will be 39. 15 position will be 40. And the 16 position will be 41. Let's circle all of these values. I've also put them in green. So we saw that we've increased from the 13th square, whatever value the 13th value would be, by 1, and we kept that up throughout. So we had 36 in the 12. Now we've got 13. Position 13 is 38. Position 14 is 39. Position 15 is 40, then 41. And I've circled them all. So what is happening here? Let me show you. In any magic square, obviously, we add up everything across, down, and diagonally. And if you have a remainder 1, it means that if you don't handle that remainder, and we just started from 25 and we kept going, and instead of 38 here we had 37, 38, 39, and 40, we would come up 1 short in the value. In other words, we wouldn't get 131 because the value we're working with, remember, was 131. So we want everything to add up to that. We would be 1 short. So what that means is that whether you're adding up any horizontal row or any vertical column or any diagonal, you have a sum of 4 numbers. And so that means that in each of those positions, you have to increase one of those numbers by 1. And if you do that from the 13, that solves the problem. So you notice that in this horizontal row, we have a number in green, which is increased by 1. The same in this horizontal row, the same in this horizontal row, the same in this horizontal row. Now, if we go down, we look at vertical columns. We've got a green one here that's increased by 1. In this column, we have a number in green increased by 1. In this column, we have the same. In this column, we have the same. Now, if you look at the diagonals, you see again that that is taken care of. So this makes sense. It should work, but let's be sure. All right, now this is where, if you don't like doing calculations in your head, you get yourself a calculator, but we'll just do it the old-fashioned way.
So if you got 5 and 6 here going down, that would be 11, so you would have a 1 here. And you're going to carry a 1, so the 2 becomes 3. So you've got 3, 6, 9. 9 plus 4 is 13. So that one checks out. So here, let's do the same thing. 9 and 1 is 10, and then 8 and 3 is 11. So what's 10 and 11? It's 21. And you're going to carry a 2, so you'll have 2 plus 3 is 5, 8, 11, 13. Checks out again. Let's come over here. 5 and 6 is 11. Okay, and then 9 and 1 is 10. Again, what's 10 plus 11? 21. Carry the 2, so 2 and 3 is 5, 7, 11, 12, 13. 2 and 8 is 10. 7 and 4 is 11. Again, 21. Carry the 2, 5, 8, 10, 13. Yes, I know. It works. So, let's go across. If we go across the same way, 2 and 5 is 7. If we're adding the ones column, and we don't have a column here, so column-wise, we just have to sort of think. 2 and 5, I mean, we can do it various ways, but most people, if they did it by hand, they would do it this way. So 2 and 5 is 7. 7 and 9 is 16. 16 plus 5 is 21. So we got a 1 over here. We carry the 2. So 2 and 3 is 5, 8, 11, 12, 13. Check. 8 and 6 is 14. 14 plus 1 is 15. 15 plus 6 is 21. Carry the 2. 5, 7, 10, 13. That checks as well. 7 plus 1 is 8. 8 and 3 is 11. Put down a 1. Carry a 1. That 2 becomes a 3. 7, 10, 3, 13. That's also 131. 4 and 9 is 13. 13 plus 8 is 21. Carry the 2. So that becomes 5, 7, 9. 9 and 4 is 13. 131 again. Diagonals. 2 and 6 is 8. 8 and 3 is 11. We'll put down our 1 here. 2 and 6 is 8. 8 and 3 is also we carried a 1. So that's 1 plus 3 4. 6. 6, 9, 9 and 4 is 13. So the diagonal also checks out to 131. Last diagonal to check. 5 and 1 is 6. 6 plus 1 is 7. 7 plus 4 is 11. Then we carry a 1. 1 and 2 is 3. 6, 10, 13, 131 on this diagonal as well. So it all works.
Let's do another example. There is, let's try some really big numbers now. Work our brains a bit. Let's say you have the divine name Al-Mughni. So we, as in the case with Salam, would have been As-Salam, but you drop off the Alif and Lam. So that is Mughni. Okay. Salam. Okay. Mughni. So we're gonna have Mim, Ghain, Noon, and Ya. So this will be 40, 1,000. Mim is 50. Ya is 10. So that gives us 40. Then we have 1,000. Be sure you line up your digits very carefully. 40 and 1,000. Then we've got 50. And then we have 10. Well, this is easy enough to add up because basically we've got 40 and 50 and 10 is 100 and we have 1,000. So the answer is 1,100. 1,100. Okay? Now this number must be reduced by 30. So if you take 30 away from 1,100, you get 1070. 1,070 if I'm not mistaken. 1,070 now has to be divided by 4. So let's do that. 1,070 divided by the number 4. Oh boy. Well, let's see. If we go into 107, if we do 26, then that'll be 104. And that should leave us with 3 here. And we bring down the zeros, so we'll be left with 30. Then 7 times 4 is 28. And then if we do that, we're left with 2. So it's 267 remainder 2. Golly, what a messy number that is. I mean, it's a big number, but we can work with it. So we need to start with 267, but in cell number 1. But we have a remainder of how much? We have a remainder of 2, I think. Yes, is that what he said? Yeah, it's a remainder of 2. So that means that we have to increase from the 9th cell. So we want to come over here and circle the 9th cell. From that point on, we need to increase everything by 1. All right? So we start with 267 in this first cell. When you have these 3-digit numbers, it's sometimes hard to fit them in, so I write diagonally. So we have 267. Tamam? 267. Then we would have 268, 269. Where's 4? Yeah, it's over here. 270. You really got to keep track of what you're doing. 67, 68, 69, 70. So this will be 271. Then we'll have 272. 273. And then we would have 274. Now, when we come to cell 9, we would have had 275. So obviously we can't do that. We've got to increase that by 1, and then it'll be 276. Then when you go to 10, it's going to be 277. Let's circle this guy as well. 277. Cell 11 will be 278. 279. 280. 281. 282. And 283. Now I want you to take a moment and look at this very, very carefully. Look at it very carefully. Yeah, take a moment. So now you notice that if we had not done this, and if from the 9th cell we had just gone ahead with 275, every horizontal row, vertical column, and both diagonals would be short by 2. Would be short by 2, and we wouldn't get the value of 1100. Instead, we would get the value of 1098. But you notice that in every horizontal row, we have 2 numbers now that are in green. You see? And the same for vertical columns. We've got 2 numbers in green, and the same in the diagonal. We've got 2 greens and 2 greens on each diagonal. That means that we've taken care of that because each of those numbers has been increased by 1, and then when you add them together, the overall effect is that the sum of the row has been increased by 2. So it should work. You going to believe me, or should we check? These are much larger numbers. So I think that if you want to use a calculator here, you could do that. I'm not going to do that, but I have worked this out, and this is absolutely correct. But I want you to take out a calculator or do it on screen and check for yourself. So if we go across, we'd have 274 plus 278 plus 281 plus 267. And that indeed will give you a sum of 1100. Then if you've got 280, 268, 273, and 279, again, you should get 1100. Then 269 plus 283 plus 276 plus 272 will give you 1100. And the last row, you've got 277 plus 271 plus 270 plus 282. Here too, you should easily get 1100. Going vertically, you will also have 1100. Just going to write in the values. Don't believe me, work it out. So I don't want to spend time on a video just me sitting here working on a calculator or doing any more math. So take a moment. If you want, you can pause the video here and check, and I'll do a final example. I'll do a final example in which we have, I think, we need to do a remainder 3 example. So I'll do a final example in which there is a remainder of 3. We'll try and use one which is a bit easier to work out in your head. So if you want to pause the video and check this, please do so now. Okay. If you've paused the video, or if you haven't, you want to check it later, that's your business. We'll go on with the next example. Let's take the divine name Al-Mu'ti. In case you're wondering, since if you don't know, Salam means peace. That's the divine name. Salam Mughni is the enricher, and then Al-Mu'ti is the one who confers, who gives anything and everything. So again, we would take off the alif and lam, and mu'ti then would be mim, ain, mu'ti. Yeah, so what happens here? Well, we've got the letter Mim. We have the letter Ain. We have the letter Ta. And again, we have the letter Ya. Arba'in. Sab'in. Tis'a ashara. So here we have 40. Ain is 70. Ain is 70. Ta is 9. And Ya is going to be 10. Let's add it all up. What do we get? Well, we got a 9 on this column. And this is easy enough. 4 and 7 is 11. 11 plus 1 is 2. So we have a value of 129. So what happens? Remember, our subtraction factor is 30. Well, how would you do that? Well, if you take off 29 and take off one more, you're done. So if you take off 29, it's 100. Take off one more, you've got 99. So how does that work? From this point, we divide by 4. How does that work out? Doesn't work out. So how many times does 4 go into 99? Well, if you multiply by 24, you'd get 100. If you multiply by 25, you'd get 100. So let's multiply by 24. If we multiply by 24, we're going to get 4 less than 100, which would be 96. Where 4 times 4 is 16. You carry the 1. 2 times 4 is 8 is 9. 96. Subtract that off. And what you get remainder 3. Not surprising. So we have 24, remainder 3. So that means if we go all the way back up here, that remainder 3 means you add 1 in the 5th cell. Wow. So let's go over here and circle the 5 so we don't forget. So the numbers are going to increase very, very early on. So we start at the 1 position with, what was it? 24 remainder 3. So we start with that number, 24, 25, 26, and number 4 is 27. So right away, we have to make an adjustment from the 5th square on. So instead of 28, we're going to write 29. And I want to use the green from this point on. So we have 29. Then in the position 6, we have 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, and 40. Once again, let's look at this. Since we have a remainder 3, that means that in every horizontal row, vertical column, and both diagonals, if we don't increase, if at position 5, we just gone 28, and then in position 6, 29, and so forth to the end, we would come up short 3 in every horizontal row, vertical column, and both diagonals. So we need 3 green numbers, so to speak, in every horizontal row, vertical column, and diagonal. And you see that that is indeed the case. We've got 3 green numbers, 1, 2, 3 green numbers, 1, 2, 3 green numbers, 3 green numbers. Vertically, we have 3 green. Here also 3 greens, 3 greens. On the diagonal, you got 34, 40, 31. That's 3 greens. And here also you have 3 greens. So that means that each of these green numbers is increased by 1, which means the net increase in any diagonal or any horizontal row or vertical column will be increased by 3, so it should work out. These are smaller numbers, so let's do the math. In our head, I think we can do it. 2 and 5. Let's go here. 4 plus 6 is 10. Okay, what's the value we want? 129 is what we want to get, right?
So 4 plus 6 is 10. 10 plus 9 is 19. So this will be 3, 6, 9, 12. 129 works. 8 plus 1 is 9. And then plus 3 plus 7, that's 19 again. Carry the 1. So we have 3, 6, 9, 10, 11, 12. 129. Doing the same thing here. 5 and 5 is 10. Plus 9 is 19. Carry the 1. So 1, 3, 4, 6, 10, and 12. 129. 2 and 7 is 9. 9 plus 6 is 15. 15 plus 4 is 19. Carry the 1. So we have 1, 3, 4, 7, 9. 9 and 3 is 12 is 129. So vertically it works. Going across here, 2 plus 5 is 7. 7 and 8 is 15. 15 plus 4 is 19. Carry the 1. So 4, 7, 10, 12, 129. 7 and 5 is 12. 13. 13 plus 6 is 19. Carry the 1, so that'll be 4. 6, 9, 12. 129. 6 plus 0 plus 3 plus, so that's 9. 2, 4, 6. 6, 9, 12, 129. 4 plus 9 is 13. 13 plus 7 is 20. Plus 9 is 29. So now we're carrying 2. So it'll be 2 and 3 is 5. 7. 9, 9 and 3 is 12. 129. Diagonals. 4 plus 1 is 5. 5 plus 4 is 9. Again, 4 plus 1 is 5. 5 plus 4 is 9, so nothing to carry. 2 plus 3 is 5. Plus 4 is 9. 9 plus 3 is 12. 129. Going across here, 2 and 5 is 7. 7 and 3 is 10. 10 and 9 is 19. So we're carrying a 1. 1 and 3 is 4. 4 and 2 is 6. 6 and 3 is 9. 9 and 3 is 12. 129.
And once again, you see that it works. So these squares, these arrangements of numbers, these awfaq or so-called magic squares are really quite remarkable. They exemplify remarkable mathematical properties, and they indeed have a very, very profound symbolism, which is beyond the scope of these videos, this video series, to deal with. But there are many interesting writings on the symbolism of numbers, which are available, available in translation, such as Iamblichus, as Theology of Arithmetic. There are various things which are available also in the writings of René Guénon. There are a lot of interesting things spread around there. So this is basically all I have to say on the 4x4. The 5x5, I will do one more video, and that will be devoted to the 5x5. And I'll do it in the same sort of format, explaining what the basic square is and then how to deal with the remainders. And I think I'll probably conclude my Magic Squares series there. If people are interested, you know, I could maybe make other videos. Do let me know in your comments if you're interested in higher order Magic Squares from 5 and above. So, in fact, in traditional Islamic theurgy, the squares from larger squares from 5 onwards, like 6, 6x6, 7x7, 8, all the way up to the 12x12 are used. But the basis for all of these are the 3x3, the 4x4, and the 5x5. Those are absolutely basic. And some of the larger squares can actually be decomposed into these smaller components. So, for example, the 9x9 square, would have 81 cells in it, but it can be decomposed into 9 3x3s. And they have very interesting properties, and they're very interesting to construct. In case you're wondering, what's the largest magic square that was used in Islamic theurgic practices? That is the 100 by 100. I've actually never made one of those. That might be fun. I mean, if people are interested, maybe we could construct one, make that a video on that. It would probably have to be several videos because it's very hard to put together. Imagine, so if it's 100 by 100, that means what? That means you've got 100 times 100, that's 10,000. You'd have 10,000 cells. That's a big square. I have constructed larger squares, you know, but nothing like the 100 by 100. I did a 20 by something once, some kind of 20, a 27 by 27 once. It took me several hours, but it's very interesting, and there are many fascinating properties of numbers there, so I hope this generates some interest and people start fiddling around with these. So get some graph paper, get out your calculators, and experiment with trying to encode different numbers in different size squares. Thanks for watching.